When discussing Earth's magnetic field, it's important to remember the magnetic field extends out beyond Earth itself into the space around Earth. Now, magnetic fields, famous for interacting with other magnets, but it turns out in physics, magnetic fields were first discovered because they interact with moving electric charges. Magnetic fields, for example, exert forces on moving charges. That's how electric motors work. You run electric current through a coil wire in a magnetic field, and it creates a torque that turns it. You can likewise make magnetic fields. We talked about the dynamo effect. You make magnetic fields with moving electric charges. Changing magnetic fields can also produce electricity. That's how the alternator in your car makes electricity. Basically, almost all electricity that we use in this country is really made by coils of wire that are spinning in magnetic fields. You just use different kinds of energy to turn the coils of wire, whether it be hydroelectric or steam. You get steam by boiling water. You can boil the water with wind. You can boil the water with oil or gas that you burn, or even by nuclear power. Any of that makes steam, which spins turbines, which spin coils of wires in magnetic field, make electricity. Wind power generates magnetic field by the wind simply turning turbines that are keyed to gears that turn coils in magnetic fields. And again, this is how the alternator in your car makes electricity. And the battery just stores it. It doesn't really make electricity. The alternator makes the electricity, and it does it by having coils of wire spinning in magnetic fields. So all these properties interact with each other. And so what happens is that particles in deep space can get caught in these magnetic fields and bounce back and forth in the magnetic fields around Earth. And so if you happen to have a spacecraft that was going out here and was going through where all these particles were streaming back and forth, it would blast the particles like a blast of radiation. The particles would blast the spacecraft like a blast of radiation. It turns out that the very first spacecraft launched by the United States was in February of 1958. In October 1957, then the Soviet Union launched Sputnik. And then a month later, they launched a second Sputnik, Sputnik 2, which had a dog on board. The first Sputnik basically just orbited Earth and had a temperature sensor. The second one had a dog on board to see how organisms live in space. Turns out the dog didn't live very long. The Americans launched a spacecraft called Explorer, however. Explorer 1, the first of a series. There's actually been a bunch of Explorer spacecraft, several dozen of them. But the first one was launched, and it was the very first successful space launch by the United States. It's a small unmanned thing, and about the size of a large tube, just a few inches across and a few feet long. But on board, when they launched it, James Van Allen, a scientist from Iowa, had an idea of putting a Geiger counter on board to measure radiation outside of Earth's atmosphere. And as the thing launched, it discovered these large regions of intense radiation circling Earth. And we call these the Van Allen radiation belts. And so the Van Allen belts are these are basically charged particles bouncing back and forth in the magnetic field. They make these donut-shaped regions encircling Earth. There's more than one of them out here. Now, ideally, you don't want to be in them if you can avoid it. So the International Space Station orbits very low orbit just underneath the Van Allen belts. And so that's the idea, so you try to stay below them, because passing through them gives you a substantial radiation exposure. We'll talk more about that later, but the thing is that what can happen is that solar wind, which are particles streaming from the sun, can impact the Earth's magnetic field. Now, the Earth's magnetic field dominates space in a region near the Earth that we call the magnetosphere. So Earth's magnetosphere extends quite a ways out, and the Van Allen belts are part of that magnetosphere. And so what can happen, though, is that, of course, the solar wind is pushing this way. The Earth's magnetic field exerts forces. These charged particles, they slide around this way. They bunch up in front of the Earth, something that we sometimes call a bow shock. And this bow shock, if you pass spacecraft through there, you get a blast of radiation like in the Van Allen belts. And most of these charged particles, drag off behind Earth. There are a few that leak into the magnetosphere. They get caught in the Van Allen belts. Magnetosphere has this big, long magneto tail that sticks off here. The magnetopause is the boundary between the region of space where the Earth's magnetic field dominates or where the sun dominates. Satellites orbiting beneath the Van Allen belts, interestingly enough, still have radiation exposure sometimes. And since the early days of space exploration, they noticed that this happened a whole lot over the South Atlantic. This is actually a Dutch satellite from the Netherlands that was in orbit around the Earth, and the little yellow dots plot the places where it had a memory upset or something that interfered in the memory due to radiation. And you see the little dots all over the place, but most of the dots seem to be congregated over the South Atlantic. And so, since this happens a whole lot for a lot of different spacecraft over the South Atlantic, that region is called the South Atlantic Anomaly. So what's going on with the South Atlantic Anomaly? Has to do with the fact that this magnet that acts like it's inside the Earth is actually a little bit off center. It's not really going right through the center of the Earth. It's just a little bit off to one side. That means the Van Allen belts are a little bit higher on one side of the Earth and lower on the other side of the Earth. And so the South Atlantic Anomaly is right here, where the Van Allen belts are actually coming down very low, and so these low Earth orbiting satellites bump into the lower edge of the Van Allen belts. And so that gives you radiation exposure, which gives rise to the South Atlantic Anomaly. Again, this is like a radiation map of low Earth orbit. And you can see the South Atlantic region down there has more radiation in there because of the asymmetry of the Van Allen belts. Again, this is a graphical map showing where the South Atlantic Anomaly is. The other thing that happens, though, is those charged particles can follow the magnetic field around and slam into Earth's atmosphere. And when they do, it gives you brightening the sky that we call the aurora. And so the one in the north is the aurora borealis. The one in the south is the aurora australis. Now, there's something that can sometimes happen, and that is that the particles from the sun can sometimes come as a giant blast, which slams into Earth's magnetic field and actually can cause the magnetic field to shift somewhat. And when that happens, the Van Allen belts can shift a little bit. It can also cause excess particles to come accelerating down into Earth's atmosphere. It can move the aurora further south. I've actually seen the aurora as far south as here in Texas 3 times. It doesn't happen all that often, but it does. And these fluctuations in Earth's magnetic field we call geomagnetic storms. Geomagnetic storms have all kind of impacts. One of the things that can sometimes happen is that geomagnetic storms can cause radio signals to be blocked. So sometimes satellite signals don't make it to the ground, and sometimes satellite signals to satellites don't work. And so during a major geomagnetic storm back in 2003, for example, satellite communication was upset. That means your GPS would not work for about 3 or 4 hours one afternoon. A lot of banks or debit cards and so forth that used satellite links, they weren't operating because of the satellite outage. Spacecraft or even aircraft that are very high altitude can receive large doses of radiation. Again, during this event, what happened was that anybody in a transatlantic airplane received between 1 and 200 chest x-rays worth of radiation just in the course of the flight. They actually ended up with other sort of issues that happened as well. They actually held flights, and they didn't tell the passengers they're not going to fly because it's radioactive. They called it a weather delay. And technically this is correct because all these effects are called space weather. The space weather also influences electric distribution grids and pipelines. One thing that can sometimes happen here is you can cause power outages, regional power outages, not just local, but entire sections of the country. During a major geomagnetic storm a number of years ago, a few decades ago, almost the entire northeast of the United States and then parts of Quebec and Canada were without electricity for an extended period of time. We're talking several days because of a major geomagnetic event. It also causes excessive amounts of electricity to run up and down pipelines that are not really designed for electricity rather. And so that causes underground pipelines to degrade much more quickly than they otherwise would do. Now, all this has to do with how the Earth's magnetosphere, the Earth's magnetic field, interacts with the sun. And so we'll be getting back to that later. What we're going to be talking about now is primarily the structure of the Earth and the region and what the Earth's doing. So I wanted to mention the magnetosphere here in that context. Next week, we'll be talking a lot more about the solar terrestrial or even the Earth solar system interactions, things that impact Earth from outer space. And so we'll get back to talking about geomagnetic storms at that point.